What is the true nature of the universe? How large is it, and where does it start and end? And if it is not infinitely extending, then what else may be lurking out there beyond its bounds? These are the questions pondered by scientists and philosophers alike for centuries, as they contemplated the possibility of a parallel universe. The idea that our cosmos is not alone, but instead part of something bigger. That something is the so-called multiverse, an outlandish branch of theoretical physics that doesn't often receive much serious consideration from scientists, due to its wildly speculative and ultimately untestable nature. However, there exist a myriad of contrasting interpretations to explain how a multiverse might manifest, some of which may affect our own cosmos in ways which we can observe. So buckle up and get ready, because in this video we will be leaving the solar system and the galaxy entirely, as we take on the biggest question of them all, the question of cosmic seclusion, and whether our universe is the only one. The notion of other universes is a fascinating one to consider, forcing us to probe the deepest parts of our conscience as we contemplate our existence in the grandest context. It captures the imagination like no other theoretical concept, especially within the sphere of arts, entertainment, and popular culture. Most recently, in fact, the hugely successful Marvel franchise made the multiverse a central theme in a number of its latest blockbusters. But there's a problem, because this wacky interpretation of the multiverse theory is not one that is grounded in science or realism. In fact, cosmologists generally steer clear of the question of a multiverse altogether, for its inability to offer sufficient observational evidence to back up its many wild assertions. However, there are a number of different shapes, sizes, and forms that a multiverse may take, some of which are inspired by empirical, observational evidence which we can test for. The simplest of these interpretations, and perhaps the easiest to visualize, is the quilted cosmos, the idea that we live within an infinite universe. If the universe is truly infinite, and populated by stars and galaxies on all length scales, then anything that can happen will happen. Not only that, it will happen an infinite number of times. A genuinely boundless spatial expanse would house an unending number of Hubble volumes and observable universes, leaving room for every conceivably plausible eventuality to play out ad infinitum. Because there is only a finite, albeit very large number of ways in which atoms can arrange themselves, even at a certain finite volume, we would expect to start seeing repeating patterns of particles in space, including perhaps repeats of ourselves. But the so-called quilted model takes this to infinity, positing an endless number of parallel observable universes running in synchronization with our own, intersected by an infinite number of differing eventualities, but chiefly all governed by the same laws of physics that we experience here on Earth. According to a widely distributed 2003 publication by MIT physicist Max Tegmark, this would constitute a level 1 multiverse in his 4-tiered system of classification. A level 1 multiverse is the infinite cosmos, where galaxies just keep on going forever within a boundless spatial expanse, rendering it entirely impossible that we are the only intelligent civilization in space. Astronomers have pondered this possibility for well over 2,000 years, but the true size of the universe is shrouded by the cosmic light horizon, the spherical, shell-like curtain of darkness that lines the edge of our observable universe, beyond which we are unable to see any further. But of course, most of the evidence we've accrued from within this observable frame points to a finite expanse, whatever size that may be. The existence of the cosmic horizon itself implies a finite age for the cosmos, as does its oldest detectable light signal, the cosmic microwave background, which was emitted only shortly after the fiery birth of space. And given its apparent expansion ever since, we've good reason to believe that the universe has a finite, quantifiable volume that increases with time, destined never truly to breach infinitude. That being said, there is one cosmic property that we've plucked from the CMB, which is more characteristic of an infinite universe. Its seemingly near critical density, and accompanying absence of any significant spatial curvature. Our cosmos, even on the very largest of observable scales, appears to be flat, meaning its geometry does not curve round to close itself off, as we would expect of a spherical, finite universe. Rather, a flat geometry is the one we'd expect to find in a universe that is indeed infinite, and where 3D space applies on all length scales without curtailment. It's certainly an intriguing possibility, and one which we can never conclusively rule out. However, cosmologists don't generally roll with the idea that the universe is infinite just because it seems flat and critically dense. Rather, they have another explanation for these peculiar properties: cosmic inflation. The inflationary theory asserts that, only a few instances after its inception, our universe underwent a very brief but vigorous period of exponential expansion, driving it to the immeasurable scales we associate it with today, before the events we know as the Big Bang had been set into motion. Back then, the laws and metrics governing space were still undefined, and thus there was no natural restraint to hold back the rogue, embryonic universe, as it scaled itself up in volume by at least a factor of 28. It happened so fast that the primordial contents of the infant cosmos was also resized with impeccable smoothness, preserving its critical density by leaving no time for mass density gradients or disparities to occur. And once this inflation ended, the energy driving it reheated and decayed into the plasma soup that permeated our very early universe, where the events associated with the more conventional description of the Big Bang ensued. This idea was first tabled all the way back in the late 1970s by MIT physicist Alan Guth, as he attempted to plug the handful of remaining holes troubling the emerging Big Bang model of cosmology. In fact, though it makes up an immutably important part of our standard model today, cosmic inflation wasn't really incorporated into concordance cosmology until the 2000s, following the discovery of a similar expansionary force known as dark energy, which seems to be accelerating the universe's rate of expansion while balancing out its force of gravity. Before that, however, inflation was seen as a wildly reaching attempt to prop up an incomplete Big Bang model, and was reworked independently by several other scientists in the years that followed. By 1983, theoretical physicist Paul Steinhardt discovered that, consistent with newer descriptions of inflation, the underlying expansionary field may not have subsided universally, and that our observable field may represent only a small, localized lapse which fragmented from the expansionary force. But elsewhere in the cosmos, cosmic inflation may continue to this day, destined to eternally give rise to an exponentially expanding volume, ultimately rendering an infinite cosmos in the infinitely far future. This interpretation of events is known as eternal inflation, and it is crucial for us in understanding our first instance of a level 2 multiverse, an inflationary multiverse strewn with hot bubble universes across its expanse. In an eternally inflating universe, where the majority of space never stops undergoing this exponential expansion, new embryonic bubbles would continuously break off from the wider inflationary field with time, and thus, after an eternity, every conceivable bubble universe will have played out somewhere, just as they would in a level 1 multiverse. But this time there's a twist, because unlike with level 1, where the same laws of physics apply everywhere, the post-inflationary bubble universes of a level 2 multiverse would have taken shape at different times, and would thus have experienced their own unique set of preconditions when undergoing their big bangs. This may have resulted in them experiencing certain processes of the early universe, such as symmetry breaking, which established the 4 fundamental forces in a different way, culminating in a cosmos with different laws of nature. Everything from the speed of light, to the strength of gravity, and even the charge of subatomic particles may be reprocessed with each new inflationary bubble, yielding a multiverse with far more physical variety and diversity than we'd find in an eternally infinite cosmos. From familiar Earth-like realities to turbulent, starless voids ruled by chaos and instability, along with everything in between. Thus, we have our first instance of a level 2 multiverse, a landscape multiverse constituting an overarching spatial expanse proliferated by regions with varying laws of physics. Indeed, level 2 gives us a lot more theoretical headroom for possibility, with its other interpretations just as captivating and mind-bending to consider. Among them, the notions of a previous universe, a population of universes, and even a plane of higher dimensional space. Let's start with a previous universe, as we contemplate the possibility that our cosmos is just one go-round, in an eternal, self-sustaining cycle of universes birthing and dying, playing out every possible scenario over time to give us our next flavour of multiverse. Though nothing lasts forever on this planet, many of its life processes play out in a cyclical fashion. We are born from dust, and to dust we eventually return, only to sow the seeds for something new in our place. This begs the interesting question: could the nature of the universe be cyclical? The first to formalise this possibility was the Russian meteorologist Alexander Friedmann, with his model of an oscillating universe in 1922, starting out with a Big Bang and period of expansion, followed by an eventual contraction under its own gravity which culminated in a big crunch, before rebounding and repeating the cycle anew. This notion was toyed with by scientists including Einstein himself for over a decade, up until 1934, when American physicist Richard C. Tolman cast doubt over the theory, by highlighting entropy as one of its key stumbling blocks. Because of the leaky nature of thermodynamic energy exchanges in our universe, Tolman found that the quota of waste energy in the closed-loop system cosmos would need to increase with each cycle, implying a directionality to this supposedly eternal process. Greater entropy would lead to a larger and more expansive universe with each repetition, and one which is harder to rein in with a gravitational collapse. And if we extrapolate this trend backwards to shorter cycles, we eventually reach a point where the model breaks, as the Big Bang stops birthing a new universe. As such, Friedman's oscillatory model was shelved, and come the end of the century, cyclical interpretations received yet another near knockout blow, with the revelation that the universe's expansion is accelerating, not slowing down en route to contracting. But there are cyclical models which don't require cosmic contraction, such as Nobel laureate Sir Roger Penrose's theory of conformal cyclic cosmology, which revises the Big Bang as the final event occurring within the remote future of a previous eon. A progenitor universe that has become so old and vast that its contents was entirely reduced to energy and massless photons, rendering scales such as distance and time meaningless, and ultimately indistinguishable from those we associate with the birth of our own universe. If this is the case, and the Big Bang merely reset our cosmos as opposed to resizing it, then proponents argue that certain signatures from the previous eon may have carried over into our universe, namely the ghosts of its ultramassive black holes, which evaporated into Hawking radiation that was then caught up in the conformal rescaling event, and etched into the CMB as ring-like formations of high-energy photons. And while the jury is still out on that one, black holes may yet hold the key to understanding the nature of our universe in the wider context. If the universe is not part of a cycle, then perhaps it is one within a population, specifically a family tree-like hierarchy of parent and child universes, ruled by natural selection. In 1992, American theoretical physicist Lee Smolin proposed a theory entitled the Fecund universe, which models our reality as just one node amongst an enormous hierarchy of related universes, which reproduce through their black holes. The theory states that whenever a new black hole of any size is formed, the cradle for a new cosmos is laid beneath its event horizon, a place where space and time pinch off to run independently from their parent. The matter and energy consumed by this black hole thereafter is then crushed into a sample, for recreating a new seedling universe inside, which is then left with all the time and space it needs to bounce back into its own cosmos, totally disconnected and blissfully unaware of the space that lies beyond. The theory overlaps with that of black hole cosmology, which posits that our own universe exists inside the causally disconnected confines of a black hole, and in turn explains the problem of our universe's complexity by supposing that its curious set of finely tuned properties are in fact inherited, having been primed by the process of cosmological natural selection. Every time a new universe is born from a parent's sample, the recipe for reality is slightly reprocessed, and laced with minor departures from the progenitor, just like in reproduction here on Earth. And with a means of evolution, the tree would soon tilt in favour of universes with laws of physics like our own, which enable black holes in space-time on a variety of scales. Before long, cosmic natural selection would have waded through swathes of poorly tuned, unspecialised universes with unsuitable laws of physics, to arrive at an almost flat, critically dense cosmos filled with billions of stars, galaxies, and thus black holes. Taken together, this hierarchy represents our next take on a level 2 multiverse, one where the true extent of reality is an uncountable aggregation of interlinked, reprocessed universes, and not just one big partitioned spatial expanse, as with previous interpretations. On the one hand, this family tree may be infinite, with no conceivable beginning or end, bustling with every possible scenario along the way. On the other hand, the tree may be finite, but a closed-loop system of cosmoses which ultimately create themselves, enabling their eternal repetition without the need for infinitude. Either way, we are certainly starting to ascend from more grounded science into the realms of wildly speculative, but still equally as intriguing interpretations of parallel universes. And for our final take on a level 2 multiverse, we need to stray even further from convention still, as we dive into the convoluted realm of string theory. String theory is another branch of theoretical physics, which offers its own unique take on reality as a means of producing a theory of everything. That is, a single mathematical framework which can unify the behaviour of atoms in quantum theory with those of gravity in Einstein's relativity. It attempts this by reassessing the most fundamental building block of nature, positing that reality is composed of tiny, Planck-scale length one-dimensional cosmic strings, which vibrate like little instruments to yield the conventional particles building up our cosmos. Furthermore, string theory posits that these vibrations occur across many extra dimensions than the standard 3 of space and 1 of time experienced by us. In fact, it asserts at least 6 additional spatial dimensions which exist on microscopic scales far too small for us to gauge, and what we experience as reality is simply the result of our dimensional tune, configured to a specific combination, like an old television set to one of many radio frequencies bouncing around a room. And elsewhere in this room, other unique dimensional configurations may also be propagating as their own sheet-like brain universes, in the wider expanse of higher dimensional space, yielding a multiverse underscored by an even broader plethora of physical variety and variability. One of the core assertions of brain cosmology is that gravity is multiversal, streaming all over hyperspace in the form of graviton particles, which facilitate interactions between disparate brain universes. In fact, one of the more popular interpretations, the ekpyrotic model, proposes that the Big Bang was actually the result of a collision between 2 parallel brains, which released the insane heat and energy that decayed into our universe's early contents. And similarly, trillions of years from now, the ekpyrotic model also supposes that tension between the 2 brains will eventually bring them back in for another collision, reining in and contracting space-time, ultimately en route to a big crunch. It is also a cyclical model. Elsewhere in hyperspace, there may be an incomparable number of differing dimensional tunes manifesting as their own realities. The M-theory interpretation, in particular, posits 10 dimensions of space and 1 of time, which could be curled up and configured any one of 10 to the power of 272,000 different ways, a number so big it would take up nearly 80 pages of a Word document at size 12 font, each one its own potential universe, existing somewhere within the vast string theory landscape, our ultimate instance of a level 2 multiverse. A level 3 multiverse, on the other hand, does not deal with string theory or any hidden dimensions. It deals instead with quantum theory, as we wade into the bounds of the confusing quantum multiverse. As we touched upon earlier, quantum theory is our framework for describing and predicting the behaviour of subatomic particles, which propagate on scales where conventional theories like general relativity no longer apply. It is one of the most important theories of the modern age, as its understanding of electrons informs the designs of semiconductor chip technologies, as well as all the electrical devices implementing them. And yet, the theory is plagued by a glaring departure from reality, which has frustrated scientists like Einstein and Penrose for over a century. In simple terms, quantum theory tells us that a particle can occupy two or more states at the same time, when it is not interacting with the outside world, manifesting instead as a stream of probable states, like a waveform with multiple peaks. These are known as superpositions, and they are not a principle we see carried over to the universe at large, representing perhaps the biggest obstacle for scientists trying to develop a grand, unified theory of everything. It is only when a particle is observed, or rather when it begins interacting with other particles, that its quantum properties are lost and it begins behaving in a more predictable manner, cancelling down and choosing a single state on the basis of probability, like a perfectly circular ripple coursing across a pond whose shape is only lost when encountering other ripples. This is known as the collapse of the wave function, and it is the solution to the superposition problem according to the Copenhagen interpretation of quantum physics, the general set of rules and principles most scientists accept. The alternative approach to quantum theory, however, proposed by Hugh Everett in 1957, is the many worlds interpretation. And it is this school of thought that informs our level 3 quantum multiverse. By rebuking the collapse of the wave function, Everett proposed that the universe itself has superpositions, but rather than being lost each time a decision is made, every possible scenario does play out, but as its own, disconnected universe running on a different timeline, with reality splitting in two and diverging at every possible quantum crossroads, yielding a plane of existence where anything that can happen will happen as its own cosmos, with an extraordinary level of granularity. Not just the alternate universes where you make different choices, or where the dinosaurs never died out, but also universes for every single one of the 10 to the power of 80 potential quantum states for every cubic meter of space, as well as one for every possible random movement made by the tens of trillions of individual cells in your body. What we wind up with is a level 3 multiverse of near infinite possibility, visualized as an incomprehensibly vast mathematical tree of incalculable size and depth, but where every reality is governed by the same laws of physics, as in a level 1 multiverse. Skeptics of this interpretation argue that it is an obscenely inefficient way of handling reality, with the tree quickly becoming biased and unbalanced as it clusters around certain, more taxing quantum calculations, such as the sapient decision-making and endless possibility we face in each of our everyday lives. But no matter how many possibilities there are, any finite number of universes is infinitesimally small next to true infinitude, and is thus no more inefficient or wasteful than the final form a multiverse may take, a level 4 multiverse featuring the ultimate ensemble of realities. At level 1 and level 3, the guiding line for drawing up realities is physics, and the physics governing our universe today. At level 2, this recipe is tweaked slightly, even more so when it comes to string theory interpretations. But at level 4, the guiding line is just maths, and anything that is both conceivable and mathematically consistent constitutes its own universe, playing out somewhere across an infinitely vast dimensional plane. From small and simple universes where 1 equals 1 and nothing more, to vastly more complicated cosmoses than our own, an endless number of universes would exist with infinite degrees of freedom, ruled only by logic and equations. Thus, level 4 is the multiverse in its truest and grandest sense, and the kind of interpretation featured so often in popular culture. The danger with this approach, however, is that it requires taking our mathematics in the most literal sense, believing it to be the one true coding language of the cosmos, and not just a shorthand we've drawn up to describe it. It would mean that the universe itself is mathematics, and our entire reality, including Earth and its sapient consciousness, is describable in 2-dimensional terms, which could theoretically be recreated by a sufficiently advanced quantum computer. If this is the case, and consciousness is indeed programmable, then it is plausible that our entire reality exists within the confines of a simulation, being carried out for the benefit of a higher dimensional, technologically adept species. The simulation hypothesis is perhaps the most popular application of a level 4 multiverse, as simulated reality would facilitate the creation of anything that is mathematically viable. It assumes that all technological civilizations eventually reach a point of sophistication where they can simulate their own universe and fill it with consciousness, perhaps to recreate the kind of scenarios they may be seeking to address in their own reality. And within this new, simulated universe, another sapient species wakes up, evolves, adapts, and then eventually cracks the code, programming their own conscious simulations and repeating the process, ultimately giving rise to an interconnected hierarchy of simulated realities, this time with a much different joining mechanism. It's a possibility that is as chillingly dystopian as it is fascinating and feasible, and one which continues to reside on the fringe of theoretical physics, patiently watching on in the age of rapidly advancing AI at the brink of a quantum computing breakthrough. But don't worry too much, because the simulation hypothesis, like many of the approaches we've discussed today, was conceived to explain our universe's peculiar set of finely tuned properties, such as its near critical density and well-balanced cosmological constant. But there is a much simpler answer to this problem, the anthropic principle, which argues that these are the properties required for a life-bearing universe filled up with consciousness, and if it were any other way, we would not be around to appreciate it. Even if there are parallel dimensions lurking out there somewhere, there are still far too many holes plaguing the standard model of cosmology to even effectively capture the essence of our own universe. If we can overcome those and assemble a true theory of everything, then perhaps that will show us the way to unravelling the mysteries of the multiverse. And with that, I bid you good night. C signing out.